just sketching out. You've got an E field that's incident, reflected, sun's transmitted. Is there a value for the E field or not?
No.
Okay, so it's all going to be just ratios here. So if we assume that the incident E field, for the sake of discussion, has a magnitude of just 1 volt per meter. Only reason I'm doing that, sometimes it helps give you perspective. We could just leave it as E naught, but I'd have to keep on writing E naught all the way through. Then the next thing we need to do is find out the intrinsic impedance for air. Eta is simply eta naught, or 120 pi ohms, about 377. Over here, we have to find the intrinsic impedance of the actual ocean water. I'll just call it eta 2. And that's going to be the square root of J omega times mu over sigma plus J omega epsilon. Now that's the general form, and I'm doing it that way for a reason. You all agree with this, class? All right, here for ocean water, mu is just mu naught. Omega is 2 pi times 10, or times 50 times 10 to the 6. Sigma's given, and we can take a look right now and compare sigma, which is 4, to omega epsilon. So omega epsilon would be equal to really 100 pi times 10 to the 6. And then it's times epsilon relative, which is 78, times epsilon naught, and epsilon naught is about 8.854 times 10 to the minus 12. So can you tell me what this is, the omega epsilon? I'm just going to see if, that looks very small compared to 4, but you can tell me what it is, if you don't mind. It's really 10 to the 8th times 5 times 78. I don't know. I can't do that in my head. I'm just getting these values down. Anybody else? All right, that's not a, it's an order more than an order of magnitude greater than 4, or less than 4, pardon me. But you might as well just plug in the J omega and give the whole, just do the whole thing. Give me the value for this, and could you give it to me in magnitude and angle? It's going to be close to 45 degrees, but it won't be exactly 45. But it's the magnitude 9.93?
Yeah.
At about 43 degrees, did you say?
Yeah, 43.45 degrees.
Well, that's pretty close to 45. It's just about a good conductor. I mean, it's very close. So now if I have that, the next thing I need is reflection coefficient. So that's going to be eta 2 minus eta 1 over eta 2 plus eta 1. Give that to me in terms of a magnitude and an angle too. It's going to be close to -1. What'd you get? It's going to be real close to -1, or 1 at a magnitude of 180 degrees.
0.964 at an angle of 177.7 degrees.
0.964 at an angle of what?
177.87.
Yeah, that sounds. All right, just about everything's reflected, not quite though, right? Now for the transmission coefficient, I like doing it this way, 2 times eta 2 over eta 2 plus eta naught. So give me the transmission coefficient. That's gonna be about 45 degrees. But I can't tell you what the value is. It's small. Y'all know, the only thing I'm getting is transmission right now and reflection coefficient. After that, this problem sort of does itself. Okay.
0.051 at an angle of 42.42 degrees.
Did you say 0.51?
Yes.
At an angle of
42.42 degrees.
0.42 degrees? 42.42? All right, almost 45, all right. Now that you have that, the rest of this is kind of, it's done. You have an incident wave, you know the reflected wave's magnitude is gonna be just the incident waves times the reflection coefficient, right? Y'all follow me on that? We've got, you can do this in magnitude. What's transmitted is just transmission coefficient times the incident field, right? Now, if we're talking about a ratio, and I think the problem said a ratio of the amount of power reflected. So the power incident power would be equal to, because it's in air, it's simply 1/2 magnitude of E naught incident squared over A to naught. And if you want to be frank about this, you can put it in the AZ direction if you assume this is going to be the Z direction. You don't have to do this. The reflected power density, P reflected, technically is going to be 1/2 times the magnitude of the reflection coefficient times E naught incident, right? Squared over A to naught. And it would be in the minus AZ direction if we wanted to be exact. But here you can see whatever this is just the reflection coefficient's magnitude squared times the incident. So I can do it this way. I can just say it's the reflection coefficient's magnitude squared times the incident power density right here, and it would be in the minus AZ direction. Does everybody follow me on this? Now we'll get the values in a second. Everybody got me on this? Right? Now for the transmitted power density, that's going to be a little different. For that one, I have to take, again, 1/2, right? That always is that. Then it's going to be what? Now you've got to find the field transmitted, right? The field transmitted is going to be the transmission coefficient times E naught incident here, squared, right? Then it's divided not by A to 1, by magnitude of A to 2, right? This is the difference, right? Everybody follow me on that? Then you have to put what? The cosine of the angle associated with A to 2, which is almost 45 degrees, right? Take a look at that. Y'all with me on that for A to 2? And then what? Well, this is going to also technically have an e to the minus 2 alpha z component if we wanted to be correct as far as its variation versus depth. But we don't have to put that if it's just the ratio of the amount going in. And this would be in the AZ direction. All right, back to this thing. If you look at P transmitted, that's 1/2. Then I can get the magnitude of E naught incident here squared. It's over the magnitude of A to 2, right? Then it's the magnitude of tau squared, and then the cosine of the angle. And you can put e to the minus 2 alpha z if you want in the AZ direction. Now one thing you've got to be careful with, remember here, we could get away with, say, it's just reflection coefficient times squared times power density, right? Now you can't do that over there. Y'all follow me? Can't do that. So when I assumed 1 volt per meter, because it's all ratios anyway, right? If we do 1 volt per meter, then over here, this one comes out to a power density of just 1 over A to naught, and this would be just 1 squared, and it would be AZ, right? This one is going to be reflection coefficient right there, squared, whatever that is, times the incident power density. So it's just going to be 0.964 squared over A to naught, right? Times, because that is the incident power density. in the minus AZ direction. This one's gonna be a little different. The transmitted power is gonna be 1/2. Now the incident field is 1, so I don't have to worry about times the transmission coefficient, which is 0.051 squared. And then it's gonna be the cosine of 42 degrees, call it 43, over the magnitude of 82, which is 9.93. So if you can give me this and I'm gonna forget about this part, we know it's going the AZ direction. I'll forget about the e to the minus 2 alpha z. So what's the transmitted power density? We'll get the ratio in a second. Small. If that's 1/8 or not, this is gonna be a couple orders of magnitude, at least less than that. Y'all follow me what I'm doing on this stuff? Make sure you do. It's not hard to see.
Minus 96 times 10 to the minus 6.
96 times 10 to the minus 6. Technically, this would be watts per meter squared, AZ. Can you give me the incident power density? It's just 1/120 pi in magnitude.
Did we miss the 1/2 in that?
We did. 1/2, 8 my bad, and this should have a 2 too. My bad. I did, not you, I did.
The incident power at 1.326 times 10 to the minus 3.
Watts per meter squared, and that's AZ. And what about the reflected? It's gonna be close to that. It's that value times 0.964 squared. 1.2 maybe.
1.233 times 10 to the minus 3.
All right, and you can take a look at the ratio of reflected, just do it this way. P reflected magnitude over P incident. You can just tell me what that is fractionally. It's really just gonna be 0.964 squared, that's it. Whatever that is, I don't know. Anybody?
Point 9293.
All right, and then when we have P transmission over P incident, what's that? These two better add up to be 1. If they both get them. You can just take 1 minus that top one. But I want to do it with the complete. There's always some, we do some rounding, so you're never gonna get it exact. What do you get?
0.0724.
0.0724. And if you add those two, it should be real close to 1. Okay, so that's how to do that problem. Now, I want to ask you one thing. How do you get the H field magnitude in region 2? Anybody? What are we going to do? Take the transmitted field, electric field, right? That's tau times the incident value, right? Just the magnitude. And divide it by the magnitude of 82, right? Y'all follow me on that, class? You follow me or not? Remember, whenever we talk about the definition of characteristic impedance, it's a ratio of E over H in the region, right? Right? The E field in region 2 is its magnitude is tau, the transmission coefficient, times the incident field, right? but you have to divide that by 8/2, not 8/0, 8/2, which is the magnitude of the intrinsic impedance, which is about 9.93. Y'all follow me? That's how you get the H field. The reason I'm mentioning that is oftentimes what people do, they'll have an H field in the first region and then just multiply it by the transmission coefficient to get the magnitude of the H field in the second region. That's wrong. The transmission and reflection coefficients are ratios of E field, not H field. Y'all hear me? Because 8/2 will change that. Just remember that. Okay? Gotta make sure I underscore that fact. Other questions? That's a good problem. It's a problem. We're just looking at ratios and stuff, but it tells you a lot. And by the way, there's one other thing. What happens as frequency goes up? What would you expect these ratios to do? Think about it logically. What happens as frequency goes up? I'm going to give you a tip. Look at this right here. As frequency goes up, all of a sudden what? The J omega epsilon becomes larger and larger, more and more of a factor, right? It gets less and less like a good conductor. Does that make sense to everybody as frequency goes up? So in the limit, as frequency went to infinity, it would be just the square root of mu over epsilon, but that is a long stretch. But as frequency goes up, this becomes more and more of a dielectric, less and less of a good conductor. All right, so the angle here would become smaller, get closer to 0, and this value would get closer to the value of mu, of square root of mu over epsilon. All right, just keep that in mind. That's what happens as frequency. But what happens when frequency goes to 0? Do the opposite way. As frequency gets lower and lower, this is tending towards 0. Y'all see that? Everybody? And that means it's basically going to look like a perfect conductor, right? If you have a perfect conductor, technically, this isn't exactly the definition. Sigma goes to infinity. That's really not true. A perfect conductor. Have you heard of superconductors? You hear that term? A superconductor has a definition that can be interpreted as sigma going infinity, but not really. It says no magnetic field can penetrate the material. And what that does is effectively cause the surface currents to short out any electric field you'll get, or magnetic field. You literally get an effect that is like an infinite, like a conductor that's infinite. But superconductors, you're a little young for this, but did you ever hear of the high temperature superconductor? You all know at liquid helium temperatures, when we get way down there, we can get things that become superconductors, right? Even liquid nitrogen in some cases. Well, there was high temperature superconductors about 20 years ago, 25 maybe. Boy, maybe even older. Anyway, when I was doing work at NASA, I remember we got to see Ed Teller. Does anybody know who Ed Teller is? You do? All right. Does anybody know who Ed Teller is? He's the father of the hydrogen bomb. He's brilliant. And I got to see him in his old age, and he was talking about what he believed was going to happen based on history, the history of science and development. And he had a very, very clear way of saying that as the need arises for high temperature superconductors, because it is theoretically feasible, it will occur. And he did a great job of showing how he believed it would happen, and sure enough it did. Now they have powders they can turn into superconductors, but they have a limit for the actual magnetic field strength that they can support a superconducting behavior. All right? These are crushed powders. It's amazing. He predicted it. He was right. He hit it right on that. He hit the nail on the head on that one. Now they were talking about room temperature superconductors. Why would that be of interest to you, by the way? What do you know anything about? How many of you know what a superconductor is? Heard the term, seen anything? What's the one thing about a superconductor when they pour liquid helium on superconductors that is neat? You can levitate metal. All right? What'll happen is you can take a penny or anything like that, put it on top of it, it'll levitate. All right? Now, think about high-speed rails. You know the maglev rails they have over in Asia and some of these places? Well, that takes a lot of electricity to support that, right? The magnetism. But if they had something where they could get a room temperature superconductor, at least in theory, it might make that kind of transport be super, super efficient and cheap if it wasn't too costly to make. That was the interest, but it's not an overwhelming interest. Once it becomes overwhelming, then, you know, when all the countries start throwing in money, it's like when they develop nuclear weapons and stuff like this, a nuclear weapon. When everybody's interested in it, then it happens. But when there's interests all over the place, like getting rid of COVID, then it doesn't happen. I'm just telling you, this is something to watch. I've watched this all my life. The more, if there's a real dramatic need and interest in something, if it's feasible, right, usually it happens, almost always. I mean, just think of how much has changed since 1901. We've been to the moon. I mean, if you told my grandfather when he was young we were going to the moon, he'd probably say, sure we are, yeah, you're out of your mind. But we did, right? We've got the internet. Now they're talking about literally eliminating aging. I'm not kidding about this. If you know who David Sinclair is, read about him. You are in an ideal spot in life. I mean, you are at beginnings of your careers, and you're going to see things unfold probably that I can't even imagine right now. I mean, I can imagine a lot, but I'm really going to be amazed at what happens. I know you're just looking for you. Get done with finals, go have fun. I'm thinking about this, and I'm amazed at some of the things that they're doing. Remember one thing I told you to. Does anybody have any more questions? Please try to take a course in AI, artificial intelligence. Find something, neural nets somewhere, and learn about it, because almost all of you will be impacted by that. I'm telling you, self-driving cars, the whole 9 yards, everything like that is happening before your eyes. And any other questions? Nothing. At some point, I expect football coaches to use AI. I even heard about, now I don't know if there's any truth to this, but I've heard that some college coaches now have some algorithmic thing that is like a pseudo AI to predict what other teams are going to do and prepare for it. Has anybody else heard this? It wasn't on Feinbaum either. I mean, it's got some merit to it. This is really getting out of control. When football gets involved, you know, the development's going to go off the charts. No other questions? I wanted to mention one thing before I give you a quiz. We have not done any type of a matching problem in a long time. I was thinking about maybe we should do one stub matching problem before we call it and do the quiz. Y'all want that? No. All right, you have one for me. You want me to just wing one together? I usually do this in this class for one reason. It's been a long time since you dabbled with transmission line matching. We'll start like this. We got a load here. Got some ZL. We'll make that. Got some Z naught. Why don't we do the most likely candidate for the final, a short stub. All right, so we're going to have a stub here. It's shorted, right? It's going to have some length in the stub line. The characteristic impedance of stub and of transmission line will be the same, and we have to figure out the distance. We're going to call it D right here. This will be the length of the stub, and that will be D, just the distance from the load. And now we can come up with some loads. If you got values you want, I'll be happy to put it down. For Z naught, I'm going to put 100 ohms. And for ZL here, I'm good with anything. Do you have any?
200 plus J160.
200 plus J160. Okay, so now I'm going to have to draw my version of a Smith chart. If you got a real Smith chart, great, but okay, so what's step one? Anybody?
Normalize the load.
We need ZL, normalized load, which is simply ZL over capital Z naught, and that's gonna be what? 2 plus J what?
1.6.
All right, 2 plus J 1.6. Now, we'll locate that spot just to start us off. We're not gonna be there very long. So this is the one circle, right? If we're at 2, we're inside the one circle, aren't we? Not there, something like that. And we're at J 1.6, so this would be J1, so J 1.6 would be somewhere in here. So this would be normalized ZL, and this is just my best, that would be 0.1. That's what I'd like to see, by the way, on the final exam, where you label the point you enter as 1. The next point you go to would be 2. Now this is gonna be a shunt stub, so we're not gonna work in ZL, are we? We're gonna work in Y, right? How do we get that? 1 over that, we go, just draw a line, and this would be 0.2, which is YL, okay? Right? You wanna give me that? Let's take one. We've done this problem, I recognize the values, I just don't remember what went over this. Y'all, how many remember this problem? Good. Yeah, I wish Chick-fil-A would go public, because I take a look at the lines there. If I could only buy stock in that company, I could retire today. Do you all know what I'm talking about? If you go to the mall, Tiger Town, take a look at the lines, 25, 30 minutes, any time of day or night, just about when they're open.
0.3 and 0.24J, minus 0.24J.
So it's 0.3 minus J 0.24? Okay. Now, the next thing is what? Somebody talk me through it. I want to see how much you remember.
Rotate around.
Well, before we rotate, how about we extend this, right? Right? And why did I do that? I need a mile marker, I call it, a wavelengths towards generator marker. Can you tell me what it is here? Come on, guys. You have a problem or not?
I just have the book, I don't have the.
Okay, well, if you got the problem, I think some of you probably do. If you can get that for me, we'll get there in a second, right? But we need that marker, right? Then we have to take our compass and draw a circle all the way around here. Where we're going to be basically doing this. You with me on that? Now, our job, and it depends if I want to minimize this length or this length, right? If I wanted to minimize the through length, which would be this length, now just listen to me, okay? If I wanted to minimize that length, I'm here, and so I would want to move and hit this spot right here, which is, that's the one circle right here, R equal 1, and we would want the wavelengths towards generator number here, correct, class? And it's going to be less than that, right? Do you all agree with me? All right, we would move from here, and this is 0.2. Then we'd move to here, this point, very close here. This would be 0.3. And then whatever this value is, we take that value, subtract this value, and add a half wavelength. Do you all remember doing this, class? By the way, does anybody have this value?
0.458 wavelengths.
0.458 lambda right here. And what about this value? That's where it lands over 1.
Yeah, that was 0.170.
And that would be lambda, wavelengths towards generator, right? Y'all with me on this one? So now when we figure out the distance D right here, this distance D would be wavelengths towards generator number 0.170 minus this number 0.458. And then we got to add a half a wavelength so it becomes positive. And what's that value? That tells us it's going to be just a little less than 0.25. 0.212 lambda. The reason I said that, I know every time I move all the way around the circle back to the same point, I travel exactly a half wavelength. When I move half the circle, which is about there, right? It's a quarter wavelength, it's just shy of a quarter wavelength. All right? So, and that checks boxes, that makes sense. Now, after that, I need what? I need this value right here, right? The intersect. I know I'm gonna have a real value of 1, but it's plus J something. Can you tell me what that J something is? I'm trying to do this for your benefit, trust me. I would like to get out of here too, but I think it's incumbent upon me to make sure at least I go through this with you, because it's been so long. Anything close? We do a lot of that around here, go ahead. I've had a kid take a final exam, after, telling him, bring in compass, bring in, make sure, and by the way, for the final, bring in Smith charts, right? Bring in your favorite Smith chart, put your name on it, bring it in, bring in a good compass, straight edge, so you can do your work effectively. I'm not kidding about this. The kid just drew a Smith chart with his hands and said, oh, it's about there. If you don't have a Smith chart, at least ask me. I'll be happy to give it back.
That's like 1.5.
1.5?
Yeah.
Is that right?
Yeah, that's eyeball.
All right, so 1.5 it is. All right, now what do? We're right here, normalized, we're at the 1, right? What do we have to do? Class?
-1.
We're doing a short, right? A short has 0 impedance, right? But in the admittance domain, it has infinite admittance, even when it's normalized, correct? So in a Smith chart, where do we come in? We come in right here, that's infinite, right, class? All right, now what do we have to move to? All these values, I say below the equator, down here are negative J that we're gonna hit, right? We need to move to negative J 1.5. And negative J1 is about there, so I'm guessing minus J 1.5 is about here. So now what we have to do is figure out the distance from here to here. This has got a mile marker of 0.25 wavelengths towards generator right there. What's that mile marker?
That's a 0.354 lambda.
All right, 0.354 lambda. And so can you subtract the 2? 0.354 lambda from 0.25, which is 0.0 or 0.104. Now, here's the problem with that. That, I would give this to you, but if you're a 1/10 of a wavelength or less, it doesn't actually look like a transmission line. We're right on the hairy edge of where it starts not looking like a transmission line. Because the signal doesn't have time to start developing the magnetic and electric field energies in there to cause it to look like a true transmission line. But it's close, and you can get away with it for this one. So the distance here would be 0.354 minus 0.25 lambda, which is about 0.104 lambda, just about a 1/10 of a wavelength. And that would be a match. Now I'm going to have this one question. All right. That one, it minimized both the distance from the load to that connection point, right? And it minimized the distance of the stub. What if it was an open stub? What would happen? If we wanted to match it and it wasn't a short, but it was an open stub, what's the one thing that changes?
Where you enter for the
Now I start here, right? And I have to go a full quarter wavelength, right? And then add all this to it. Do y'all follow me? So that would be the difference if it was an open circuit stub. I'm not going to give you an open circuit stub. If I give you a stub, it'll be a short. I can't be more clear, right? But even then, I'll see somebody come up with a way to make that open circuit stub work. All right, we're basically done. Any other questions before you get your quiz? Now listen, the final exam is Wednesday, right? At
Noon.
At noon. How nice, we can sleep in. Anyway, I'm going to just give you 2 pieces of advice. Do the homework and quizzes. Make sure you know how to do the homework and quizzes. The way I do my finals, ask anybody that has had me. I go through the homework and quizzes, and maybe a pass test. And then anything that you need a little work on that you had problems with, you're probably gonna see on the final. And if I say it's gonna be on the final, it's gonna be on the final. Hint.